Welcome back to day 78. Today is a hugely important video. It's one that if you are struggling before the, reviewing something, you really want to know U substitution really well. So this is a video you might come back to later to check out. So today we're talking about U substitution for indefinite integrals. U substitution is integration's answer to the chain rule. So I'm going to start with some review. And we're just going to review doing the chain rule. So if I told you f of x equals sine of x cubed, and I wanted you to find f prime of x, we'd say, hey, this f of x is a composite function. We have x cubed, a function, within another function, sine x. So to do this derivative, I'm going to have to execute the chain rule. I'm going to do the derivative of the outer function, which is cosine, with respect to the inner function, x cubed, and then I have to multiply my answer by the derivative of the inside. Right? Simplifying this thing down, I get f prime of x to equal 3x squared cosine of x cubed. Now, so far with integrals, we've only been able to do power rules and other integrals of things that we recognize, right? Like, oh, the integral of cosine has to be sine because the derivative of sine is cosine. Or the integral of secant squared x has to be tan x, because I know that tan's derivative is that, right? Or 1 over x. I know the derivative of natural log x is 1 over x. So the integral of 1 over x has to be natural log absolute value x. But that's really all we've been able to do. Well, U substitution is going to open up a lot more opportunity for things to integrate. Now imagine this. What if I asked you to find the antiderivative of 3x squared cosine of x cubed dx? Well, again, an indefinite integral is simply the antiderivative plus c. Now we know that the antiderivative of this thing must be this. Right? So this has to equal sine of x cubed plus c. And again, that's not very hard since I just did the derivative of sine of x cubed. Okay? What's much harder is, what if I was given that integral and I didn't just solve out the, what I did in black there, right? How the heck are we going to figure out that that antiderivative is sine of x cubed plus c? Well, that's where U substitution comes in. Okay? And substitution in mathematics is just a way to take a difficult problem and make it easier. Okay? So let's take a look at this original problem here and see if I can figure out how to go backwards without having that solved out ahead of time. Okay, so let's take a look at this problem. Because what we don't want to do is have integrals like this. We just have to guess a bunch of stuff and waste a bunch of time, right? We want a method that's going to be quick and easy and will work and get us to the correct answer. Okay, when you're doing U substitution, what we want to look for is, anytime we're doing a difficult looking integral here, I want to look for something and its derivative to show up. So I'm going to look for something that I'm going to call a U, and I want to look for its derivative, or something close to its derivative, at least the right power, to come up. What I see here when I look at this is I identify that this integral, this antiderivative here, has an x cubed in it, and I also see this 3x squared showing up. Okay, so what I'm going to do is I'm going to identify my u as x cubed. Okay, so we want, the function to be u. We want its derivative to come up somewhere else. Okay. And this is another one. It's kind of confusing to explain, but after you see it solved a bunch of times, hopefully it'll make more sense. So what I want to do is I want to let u equal x cubed. Okay. Let u equal the function. Then what I'm going to do is I'm going to do the derivative of u with respect to x. So I'm going to do du dx. Well, if u is x cubed, du dx would be 3x squared. Then what I'm going to do is I'm just going to solve this thing for du. And eventually we're not going to write du dx equals. We're just going to say du equals. We'll skip ahead and just say du equals 3x squared dx. Okay, so I want to figure out what u equals, and I want to figure out what du equals. Okay, and what I want to make sure is that what's after my du matches what's extra in my antiderivative. Now, if you notice, I never accounted for cosine, and that's okay. There are some things that we won't account for. But hopefully when we substitute in, it'll be an integral. We'll take this from a hard integral to an easy integral. Okay? 3x squared dx matches what's in my antiderivative. So I'm going to rewrite this integral with my u substitution being made. Okay. So the first thing I always do is I put my du at the back of the integral. Now du equals 3x squared dx. So I have now accounted for those two pieces. And all I'm left with is cosine of x cubed. But x cubed is going to be subbed out for u. This integral I write should be totally in terms of u. I shouldn't see any x's left over. You never want to have a mix of u's and x's, or x's and u's. So this x cubed here is going to be changed to a u. And the only thing I never accounted for was cosine. So substituting this integral, I took it from something ugly, 3x squared cosine of x cubed dx, and changed it into something really nice, the integral of cosine u du. That's a really easy integral. That's a really easy antiderivative, right? This is indefinite, right? So I don't have to worry about the numbers. So this must equal, well, what's the antiderivative of cosine u? Well, that would be sine of u plus c. Now, since the question was asked in terms of x, my answer must be given in terms of x. Right now, my answer is in terms of u. So once I get my antiderivative, that should be easier to solve. Now I can go back and make it in terms of x. And again, what am I going to plug in for u? Well, I got a nice equation right here. U equals x cubed. So I'm just going to replace that u with x cubed, and my answer is sine of x cubed plus c. And when I look back up, that is what I had up here. Okay. Let me try another one. Okay? So I'm going to try and solve to find an antiderivative, right? I'm doing the integral of 2x over x squared plus 5 dx. Now on the surface, this looks really challenging, right? And remember, there's no quotient rule of integration or product rule of integration. So if it's not immediately obvious what the answer is, then I'm going to try our next method is the use substitution. So do I see anything in here, any part of this that's a function whose derivative shows up somewhere else? Well, when I look at the denominator here, I see x squared plus 5. Well, I know that the derivative of x squared plus 5 is 2x. But so is, I could also choose x squared, and then my derivative comes out to be 2x. But I want you to choose your u to be as big as possible. In this case, we definitely want u to be x squared plus 5. So then we don't have to worry about the plus 5. If we just let u equal x squared, then we got that plus 5 hanging around, which makes this thing a little bit more annoying. Okay. So what I want to do here is I want to choose my u to be x squared plus 5. du dx then, the derivative of u with respect to x is simply 2x. And again, I'm going to move this dx over here, and I get du equals 2x dx. Now when I get here, I notice that du perfectly matches the 2x and the dx that's showing up in this problem. So I'm going to go ahead and rewrite this integral. I'm going to put my du at the back. That du is going to take care of the dx and the 2x. All right? It takes care of the dx and the 2x. So if those are crossed out, what has to be holding place on top? Well, that would just be the number 1. And how about this x squared plus 5 on the bottom? What am I going to substitute in for x squared plus 5? Well, that would nicely be u. And look at that. I turned this difficult integral, the integral of 2x over x squared plus 5 dx, I changed that into the integral of 1 over u du. Well, what's the integral of 1 over u du? Well, we should immediately recognize that as the natural log of the absolute value of u plus c. But that's not my final answer, because I can't leave an answer in terms of u when the question was posed in terms of x. So my last step here is I have to sub in for u. Well, again, what's u? Well, it's right here. X squared plus 5. Now again, I have the absolute value, right? But if you look at x squared plus 5, is x squared plus 5 ever negative? Well, no, because squaring a number always makes it positive, or 0, right? And that plus 5 is always going to be positive. So if you wanted to, you can rewrite this as the natural log of x squared plus 5. You can change those absolute value brackets into just parentheses. You can only make that substitution, or you can only make that change if what's inside of the absolute values is always positive, right? If I had x squared minus 5, I'd have to leave it as the absolute value. I can only make that if I know that that function is always positive. If you're not sure, leave the absolute values. Now, once again, when we talked about doing integrals, I always said, go ahead and do the derivative of your answer to make sure that it matches what you started with. Right? If I had to do the derivative of the natural log of x squared plus 5, this would be a chain rule. My answer would be, the derivative would be 1 over x squared plus 5. But then I'd have to multiply by, right, that's the derivative of the outer function, natural log with respect to the inner function, 1 over x squared plus 5. And then I'd have to multiply by the derivative of the inside, which would be 2x. Right? And simplifying that, we get 2x over x squared plus 5. Which is exactly what we started with here. Okay. Now I want to show you one where it doesn't match. But it's close. Now, on the surface, this looks like a crazy difficult antiderivative to do. I got an x squared on the outside, I've got a square root, I've got x cubed plus 2 on the inside. But again, when we look at this, when we see a difficult looking one, we don't quit, we don't give up. We look to see, is there something in here whose derivative or something close to it shows up? Well, when I look at this, I see x cubed plus 2. I know the derivative of x cubed plus 2 is 3x squared. Now, that's not exactly what I have, but it's the right base and power. So I'm going to be able to make an adjustment. I can always adjust coefficients. Okay, I'll show you how we adjust our coefficients. So the greater power here is x cubed plus 2. That's what I'm going to let equal u. All right, I'm going to stop writing du dx and just writing du and then the derivative and then put dx at the end. Okay? The derivative of x cubed plus 2 is 3x squared dx. Right? So instead of having that dx underneath the du and then multiplying it over in a step, I'm just going to write du equals 3x squared dx. Now when I look, what I have in my equation is x squared dx, but my du got 3x squared dx. I want it to say something equals x squared dx. I want to make this thing match what's in the problem. Okay? So in order to do that, I'm just going to get this line out of here. If I want to make 3x squared dx, I want to turn that into x squared dx. I always think about how am I going to do that with multiplication? Well, basically, I want that 3 out of there. I just want it to say x du equals x squared dx. What could I multiply by? What number could I multiply by that's going to get rid of the 3 and have it just be a 1? Well, the number I'm going to multiply is 1/3. So I'm going to multiply both sides by 1/3. So I get 1/3 du equals x squared dx. That equation is still true because I multiplied by 1/3 on both sides. 1/3 times du is just 1/3 du. 1/3 of 3x squared dx is just x squared dx. So I want to make this match. Now it matches perfectly. So when I go to write my new antiderivative, okay, anytime we have to make an adjustment, I always write my adjustment in front of the integral. Right? It's just a coefficient, and we can always put coefficients out in front of the integral. You guys are used to that from our last standard, so it should be no problem here. I put my 1/3 at the back, at the front, and I put my du at the back. That 1/3 du takes care of my dx and my x squared. So all I'm left with is the square root of x cubed plus 2. Now that x cubed plus 2 is what I chose to be u in my substitution. But what's the only thing I never accounted for in all of this u substitution? Well, I never accounted for that square root. So that has to stay in here. And I've changed a very difficult integral into a much easier integral. The only other step I would make before I do the antiderivative is I know that u means, or the square root means to the 1/2. Now I just have to find this antiderivative in terms of u. Well, I've got 1/3. And now I just bump and divide. I'm going to bump the power up by 1 to 3/2. And divide by 3/2, which is really multiplying by 2/3. Again, even though it's a square root, it's one we can do, right? I made you do square root integrals in the last test. Now, multiplying this out, I get 2/9 u to the 3/2. So there's my answer. The problem is my answer right now is in terms of u. I don't want my answer to be in u, I want it to be in x. So I'm just going to substitute back. Oh crap, what was u? Oh nice, I have it written down right here. U equals x cubed plus 2. And that is our final answer. Now again, whenever I get to the end here, I think it's a good idea to do this derivative and make sure it comes out. Okay? So let's write the answer I got. I want to do the derivative of this and make sure it matches with what I started with. Well, let's take a look. This would be a chain rule. I have a function within another function. So a chain rule, I do the derivative of the outside. So I'm going to take 3/2 and I'm going to multiply by 2/9. I'm going to keep the inside the same and reduce my power by 1. And then I'm going to multiply by the derivative of the inside. Now this doesn't look like our answer right now, but take a look. When we simplify this down, this 2 and this 2 will cancel. This 9 becomes a 3, this becomes a 1. And I've got 1/3 x cubed plus 2 to the 1/2 times 3x squared. Well, what's 3x squared times 1/3? That's simply x squared, x cubed plus 2 to the 1/2. And like magic, I get exactly back what I started. Right, x cubed times the square root of x cubed plus 2, right here. Okay. Let me show you one more to get us ready for tomorrow. Now, this one doesn't look very difficult, but it is still a u substitution problem. Now again, you might say, wait, how is this u substitution? Right? Well, the problem is that 2. If it was just the integral of sine x dx, my answer is negative cosine x plus c, and I'm done. But that 2 puts a little bit of a wrinkle in there. Now you might say, Mr. Hartz, well, where's the function I choose for u and its derivative that shows up? Well, what's the derivative of 2x? Well, that's simply 2. Now, there is no 2 in here. However, there is a 1, and I can always adjust coefficients. So watch what's going to happen. I'm going to let u equal 2x, du then equals 2 dx. Again, I'm just multiplying that dx over. I don't have 2 dx in my problem. I have 1 dx. Well, what can I multiply 2 by to get 1? Well, my adjustment is going to be multiplying by a half. And now I make it match. So, look at my new integral. Again, I put my half at front, I put my du at back, and that accounts for dx. That 2x is going to be subbed in for a u, and this is going to say sine u. And in a sense, I just turned this from a sine of 2 times a variable to sine of 1 times a variable. I just don't want to forget about this 1/2 that's out front. Well, what's the antiderivative of sine u? Well, that would be negative cosine u plus c. Now again, don't make this your final answer, right? Your final answer can't be in terms of u, it needs to be in terms of x. Your final answer should be negative half cosine. I'm going to substitute in my u with my 2x. Now again, if I do the derivative of this thing, what do I get? Well, the derivative of negative half cosine of 2x, right? This is a chain rule, so it's going to be negative half. The derivative of cosine is negative sine of 2x times 2. Right, that's my derivative. Plus c goes away. Well, what's 2 times negative half times negative 1? Well, 2 times a half is 1. We have a negative times a negative, that makes a positive 1. So we're just left with sine of 2x, which is exactly what we started with here. Okay. That's it for today. A little bit longer of a video, but hopefully we'll be able to just attack this tomorrow on Wednesday in class. That's it for today. 2 chains, bye.